Recording in progress. I apologize for the tardiness of this video. It's a little after 7, but I just got home. I wanted to make the video first for physics. Hopefully you've all gotten the worksheet for the additional problems from somebody else in class. And so I wanted to go through these just for more practice, drawing free body diagrams as well as solving different unknowns in these different tension scenarios in preparation for the quiz, which we'll be having tomorrow. Okay, so for number one, I want to draw a free body diagram of the system. So a 4.7 kilogram bucket is suspended in a well by a rope, which is wound around a windlass. Now, windlass is, of course, stationary. It's held in place. So it's not technically moving as part of the system, which changes things a little bit from some of our other examples, but I wanted to include it in our diagram. So a boy turns the crank of the windlass to lower the bucket at a constant rate. If it's going at a constant rate, that means it is not accelerating. So we have a balanced system. So we do not have to add the acceleration here. So if I include the windlass in the system, then we have the windlass, we have the upward force. So this is just the normal force. That's what we call that opposite force that keeps you from falling through the ground as gravity holds you to the ground. And then if we are drawing the system, then we have the bucket. And then below that, we have the force of gravity on the system. Total, that's what we call the FG. So this is the free body diagram of the system. Now, if we draw a free body diagram of just the windlass, then fairly simple at this point. You have the normal force, and it has its own gravity. So you have the force of gravity. So I'm going to call that FG1. Additionally, with that, you have the tension that's created from the bucket that's hanging on this rope from the windlass. So there are multiple forces here. Because it includes the tension that's holding up the weight of the bucket. Then if we have just the bucket, we have to be really careful with this. The downward weight of the bucket is going to be the force of gravity only on the bucket. That's why it's got a different subscript, because that force is less than the force of the entire system, because it is holding the bucket, just the bucket. And then we have that tension between the bucket and the windlass, and so that's T prime. As you can see with this one, in the case of the tension, our downward tension is actually going to be negative because it's downward, and then so our tension prime is going to be positive. Okay, so the questions that we have, how many forces are acting on the system? That means it's just related to this very first diagram. So you can see we have the tension at the top, or the normal force, and then we have the force of gravity. So there's always going to be only two forces acting on the system as a whole. And then what system would be best to analyze? The windlass. That is just the windlass system. There, sorry. And the forces acting on it are, excuse me, the normal force. And of course, if the windlass was something that was hanging from a rope that had tension in it, then you would have the upward tension, the bottom tension, and the force of gravity on that object. So, but in this case, it's just normal force. The force of gravity on the windlass itself, so FG1, and then the lower tension that's from the bucket. So you have the three different forces there. All right, moving on to an actual kind of applicable problem with a little more math to it. A construction crew is roofing a house. They use a rope to pull up packages of shingles from the ground. The rope can transmit up to 500 newtons of force without breaking, and then each package has a mass of 50.0 kilograms. So if we draw a free body diagram of one package of shingles as it's being lifted, again, this is like a one object free body diagram, so pretty simple. I'm just going to go ahead and label it because we know I can't draw. And so I'm just going to use a dot. So there's our shingles. So in this case, obviously we have the tension at the top of that includes the weight and any acceleration as it's being pulled up. And we have the force of gravity on the shingles. We just have to use F of G because there's only one thing that there's only one object in the system. All right, so with what maximum acceleration can the crew raise the shingles? So in this case, they told us that the maximum force is 500. So that means that our tension, I'm going to call that tension max. Obviously, it could be different if they went slower. The maximum tension this rope can handle is 500 newtons. And then, of course, looking at our diagram, we have the force of gravity. So the force of gravity, remember, gravity is an acceleration, not a force. So we have to take the mass of the shingles, just call it MS, times gravity. So this is the 50.0 kilograms times negative 9.81 meters per second squared. And so that's going to give us our force of gravity. I'm just going to leave that like that for now. And then we have the mass of the shingles, which is 50.0 kilograms. And then we need to know the acceleration. That's what we're being asked to find. So we use the acceleration equation. Acceleration equals the sum of the forces divided by the mass. In this case, our forces are the tension plus the force of gravity. And we put that over the mass. I'll use MS since I've already done that. All right, so it's the max tension, because obviously if they're pulling it at the maximum acceleration, then they're going to be reaching that threshold. So when we plug in our values there, we have the 500 newtons plus, in my case, 50 times negative 9.81 divided by 50 kilograms. When you plug that into your calculator, you get the maximum acceleration is 0.19 meters per second squared. So that is the maximum acceleration that they can pull on this, pull these shingles up. Okay. And again, the acceleration is not the velocity. So that means they can keep increasing their speed, but only at an acceleration of essentially 0.2 meters per second squared. Okay. Now this is the one that's really kind of the meat of this exercise, and we're going to cover a lot of different things. And hopefully it'll all come out of my mouth the way it's supposed to. Okay, so we have two boxes held together by a strong wire and attached to the ceiling of an elevator by a second wire. The mass of the top box is 14.2 kilograms, the mass of the bottom box is 10.4 kilograms, and the elevator accelerates upwards at 2.84 meters per second squared. So in this case, because we're being asked to find the tension, we need, yes, we have sort of a total force. We're using the entire system because we're looking at the top box. That first wire holds the entire system, both boxes. So we have, I'm going to use the well, I'll go ahead and redraw it. It doesn't matter. So in this case, if I have A and B, let's see, I have I'm going to call that mass 1. That's our first box. Mass 2 is our second box. Coming from mass 2, that's the force of gravity on the system. And just because it works a little bit better for my brain, I have, let's see, try to get myself neat here. Goodness gracious. Okay. So this bottom one here, this would be my tension, call that T1. And then we also have the force of acceleration. So the tension only counterbalances the force of gravity on the system. And then we have that extra force that is being caused by the acceleration. So that's making the line kind of even tighter. What we're wanting to find out, we know what that force of the acceleration is. That's sort of the, the total sum of the tension and the force of the gravity of the system. And so to find the tension, let me see here. Let me just make sure I'm doing that right. Tension. I do this every time. So I'm trying to picture it, right? So if you have one force pulling up on a string, in this case a wire, and then you have another force pulling down, both of those combined are going to increase the tension. And so essentially what we're trying to get is okay, so that's what I would do. This whole thing is the tension. Like that's this little bit here is the force caused by acceleration, but the entire thing is the tension being caused by both the upward force from the acceleration and the downward force from the weight and the gravity of the two objects that are hanging. Okay. Anyway, so the key here though is if you're finding anything on the top item, you're going to have to use the whole system in order to do it. So that means that we need to know the force of gravity on the entire system. And in order to do that, we need to know the mass of the entire system. So I'm going to do that first. The first step here is I'm going to find the mass of the entire system because that's what's hanging from this wire, and that's the mass of the first box plus the mass of the second box, which is 14.2 kilograms on my way, plus 10.4 kilograms. So the mass of the system is those two combined, which is 24.6 kilograms. All right, I'm going to use that mass to find force of gravity on the system. That is the mass of the system times gravity. The 24.6 kilograms times negative 9.81 meters per second squared. So that means that the force of gravity on the system is equal to negative, I have it here somewhere, 241, there's my significant figure, 0.3. All right, so I found that. The only other thing I need to do is I need to find the force that's being caused by the acceleration. That is F A is the mass of the system times what am I doing? The acceleration. So 24.6 kilograms times the acceleration they gave me 2.84 meters per second squared. And so the acceleration is 69.86. There's my significant figures, newtons. Okay, once I have those three, I can find T1. So you can think of, I'm going to do this over here. You can think of the sum of the forces as the force of the acceleration, right? The force of the acceleration is, we have an unbalanced system in this case. So the sum of the forces is not zero. The sum of the forces is the upward tension added to the force of gravity. And then so that's created an acceleration because the tension is going, it's pulling the whole system upwards. We also know that the sum of the forces is the tension plus the force of gravity in the system. So this is why we can set up the equation that the force of the acceleration is equal to that tension plus the force of gravity on the system. Now, if I'm solving for tension, and especially since I'm kind of running out of room here, I'm going to take this and I'm going to go ahead and set it up so that it's T1 equal to the force of the acceleration minus the force of gravity on the system. And so that is 69.86 minus negative 241.3. So I'm adding these two together. So that means that my tension is equal, you get like 310 and some change. So it comes approximately to 311 newtons when you plug those two together. And so that is the tension in that top wire from point A to point B. All right, so when we're looking at the tension in the bottom wire, so from C to D, that one it changes the mass that's attached to it because the only thing hanging from that wire is the bottom box. So we have to change all of our variables values a little bit because the mass is different. So I'm going to go ahead and go ahead and draw my free body diagram. So this is just mass 2. And from the top of it, I have T2 prime, which includes the force of the acceleration. And I have the force of gravity, FG2. It's the force of gravity only on that mass. That's it. Because that wire's not holding the other mass. All right, so in order to do this, first I'm going to just kind of not jot down the fact that mass 2 is equal to 10.4 kilograms. I'm not really having to calculate anything there. But the second part is that I'm going to go ahead and find the force of acceleration. And so that is the mass M2, the mass of the second one, times the acceleration of the system. So 10.4 kilograms times 2.84 meters per second squared means that the force caused by the acceleration is, I lost it, 29.53 newtons. Obviously, these are all going to be a bit smaller because we're working with a smaller mass. Okay, the third thing I need, is I need to find the force of the gravity on that second box. So same thing, I'm just using the the mass of just the box times gravity, and that's 10.4, negative 9.81. And so F of G2 is 101.92. That's too many significant figures. 101.9. Okay, so now we use the exact same process. T1 equals FA minus FG2. So that is equal to 29.53 times 101.9. So that means that T1 is, why did I use T1? I'm sorry, don't mind me. This is T2 prime. Is going to be approximately 131 newtons. All right, so that finishes it as far as the review. The only other things you're going to want to make sure that you're familiar with are a lot of the notes that we have in your PowerPoint slides on ideal strings and the rules around those. I'm trying to think if there's anything else. And then just sort of the rest is set up of free body diagrams, which we kind of covered at the beginning of this. So this should have you pretty well prepared for what you're gonna need for the quiz. If you have any other questions, make sure you bring them to class tomorrow before the quiz, and I'll do my best to answer them. Thanks so much, guys. See you tomorrow.